Yeah, I'm happy to share my last work with my collaborator and friend Felipe Ponce Vanegas from BECAM in Spain. So I want to talk to you about the pointwise convergence problem for dispersive equations, or more precisely for the Schrodinger equation, a very popular problem in harmonic analysis. And I want to introduce also the mass transference principle as a tool to treat the fractal version of the problem, right? So that's what I want. That's what basically I want to do in these 20 minutes. So the problem of convergence is kind of easy to propose. You just take the free Schrodinger equation, and by means of the Fourier transform, very easily you can write the solution like this. So the question is whether you recover the initial datum pointwise when time goes to 0, right? And more precisely, you are asking for the minimal Sobolev regularity that you need, that the datum needs, so that you have, when time goes to 0, you have that the solution converges to the initial datum almost everywhere, right? So this was proposed by Carlson in 1980, and it has it's a simple question, but it has proved to be very complicated to answer. And actually, it has been very recently solved in 2019 completely. So almost 40 years of life, which is quite a lot. Actually, the good exponent is n over 2n plus 1. Okay, here I mentioned a couple of key results. These two are in the original ones in 1 dimension, and the rest of them, like Burgan, Douglas Lee, Duzang, these are the optimal results in higher dimensions, right? So along this talk, I'm going to talk quite a lot about this result by Burgan in 2016. But you may ask, like, why do I care anymore about this if it's already been solved, right? So the point is that this problem allows a lot of generalizations, and one of them, it's kind of a popular thing to do in harmonic analysis, right? Like once you are more or less done with the Lebesgue measure case, you wonder what happens with the Hausdorff measures, like with the fractal case. So you can always ask for the convergence property instead with respect to the Lebesgue measure, with respect to the alpha Hausdorff measure, right? Because essentially you want to have a better description of the divergence set of the solution. So this is one generalization. I'm going to talk about this. The other one is that, of course, you can ask for the same question of convergence for other equations, right? Instead of the Schrodinger equation, or in general, other dispersive symbols. So I'm going to focus on this paper by Anchu and Pierce earlier this year. They focused on this generalization of the Laplacian. So it's not the fractional Laplacian, it's another generalization. When k equals 2, you recover the symbol of the Laplacian, right? So in the work with Felipe, we combine these two generalizations, right? So we actually take this symbol and generalize the result by Anchu and Pierce to the fractal case, right? And for that, we use the so-called mass transference principle, which comes from Diophantine approximation, right? So more precisely, we give counterexamples, and that means that I can find a Sobolev regularity, and below that, convergence may fail, right? So that's what we do. So my idea in this talk is to explain a little bit how this mass transference principle works in this setting, right? And for that one, what I'm going to do is first to explain what is this Burgan's result that I was talking about before. It's the counterexample for the Schrodinger equation. It's the best counterexample you can give. I'm going to explain that, and then I'm going to use the mass transference principle to generalize that to the fractal case. And in the very end, I will just display the results that we get for these other generalized symbols. So the usual way that you prove or disprove convergence to the initial datum in this kind of problems is through maximal estimates, right? So there is an equivalence among the convergence property and this maximal bound, right? So you have the Schrodinger operator, you take the maximal function and you want to bound that in L2 or well, in general in some LP space, right? So since we want to get counterexamples for convergence, what we want to do is to disprove this maximal estimate. And for that, essentially, what we need is to build a Sobolev function such that the maximal function is large, right? And large means very large. And in a large set, where a large set, yeah?
It's equivalence or it's a weak equivalence. So
it's, what do you mean by weak equivalence?
I mean, I know they below imply the above, and the above imply the maximum equality.
This is true for L2. Yeah, this is a result by Stein in the 70s. It's called this. It's a big theorem. Like, and it's not a simple thing, but it's the Stein-Nikishin maximal principle.
I see. So right now you're saying if the pointwise convergence imply the maximum equalities, that's what's your claim.
That is true, and that is classical. I mean, that is a result from the 70s. Yeah.
Okay.
All right. So yeah, I mean, this is kind of a, like, I'm not saying anything new here. This is standard in treating these problems. Like, what you really wanted to check is if you have or don't have the maximal estimate.
So my impression is that the pointwise convergence cannot exactly imply the maximum equality. I mean, there are some convocations there, but I don't remember, or I don't know what's the convocations.
Yeah, so I mean, I don't claim I can tell you the details of it. I'm like, as I tell you, like, one of the implications that the maximal estimate implies a convergence, that's kind of easy. The other implication is not easy. It's a big theorem.
Okay.
Yeah, like, let's say that this is the big theorem. It's well known, and that's what we use. All right.
Yeah. So I know Stein's theorem, the limits of linear operators. He wrote in 1959. So a lot of paper refer to that paper for the reverse implications. But I don't know whether that's too strong a claim to make, you know. Yeah. I don't know. Okay, so you can continue. Yeah.
Okay. Yeah, like, I'm telling you, like, this is just like the theorem says that. So, anyways, this is what we want to disprove, right? Like, we want to disprove the maximal estimate. So let's go for it. Like, let me explain you what Bourgain did to build that counterexample. All right. So Bourgain's counterexample is essentially a sum of wave packets. Like, I don't really want to, like, that you pay too much attention to the actual expressions, right? It's an example. It's a function that has a scale that eventually is going to go to infinity. That's how you want to disprove the maximal estimate, and it has two parameters. Like these, for example, the distance among the wave packets, right? So this is the datum, and the set, the big set, the set that you wanted to debate, is essentially a union of balls centered at rationals, right? Like, modulus this rescaling with parameters. So why is this the good set? So you write the evolution directly of this datum, and you end up with an exponential sum, right? And to be able to deal with this exponential sum, which in principle is kind of what to do with this, right? Bourgain's idea was to force this point, like let's say x prime times d to be a rational number, and d squared times t to be another rational number with the same denominator, right? That's why we take these balls centered at rationals, because then the exponential sum turns into a Gauss sum, right? And Gauss sums, we know how much they are. They are square root of q. Right? So you count how many Gauss sums you have here, you put the value of the Gauss sum, and this is what you get. And this is what I meant by big, right? So since you want to disprove the maximal estimate, you divide it with the L2 norm and you get an expression, which depends on the parameters, right? You just want it to depend on the scale R, and R is going to go to infinity. And where does that come from? So that comes from the fact that you want the set to be big, right? So you ask for it. So you compute, let's say formally you compute the measure of the set. It's a union of balls. So take the measure of each ball and count the number of balls. You get this expression, this quantity. Of course, like this you have to justify, but this is kind of the technical part of the paper, right? But you can do it. And you force this to be 1 because you want it to cover a large portion of the unit ball, right? So here you get a restriction for the parameters. You replace it here, and you get precisely the power that you want, n over 2n plus 1, right? So this is essentially Bourgain's counterexample. So the important thing is that the set has this shape. It's a union, essentially a union of balls centered at rationals. So how do you generalize this to the fractal case? So there are essentially 2 main complications. This is related to what you say. Steins-Nikishin theorem is not true in the fractal case. So it's okay when you are taking LP norms with respect to the Lebesgue measure, but it's not true when you are dealing with Hausdorff measures. Okay, so you actually want to construct the counterexamples by hand, right? The counterexamples for convergence, and actually trying to answer again to your question, Stein's theorem is kind of a shortcut that you can use, but you don't really need it because you can always do these kind of explicit constructions of the counterexample, right? So what you want to do is to take the previous examples by Bourgain and sum them diagonally, right? You sum them diagonally, and this is gonna give you the counterexample, right? I'm not going to go into much detail here, but the price you have to pay is that now, since you have like all dyadic functions here, you need that your point is in every of the previous sets, right? Or at least in infinitely many of them. And that means that instead of just dealing with one of them, now you need to deal with the limb soup of them. And this is a complication, right? The second one is that previously it was enough to compute the measure of that set. And now, since we're in the fractal case, we need to compute the Hausdorff dimension of the limb soup. And computing Hausdorff dimensions is demanding. It's a difficult task in general, right? And for this, we're going to use the mass transference principle. So let me tell you what the mass transference principle is. As I told you, it comes from Diophantine approximation. It's a method to give a lower bound for a limb soup, for the Hausdorff dimension of the limb soup set, right? So let's consider we have a sequence of balls with shrinking radii. And our objective is to, as I said, to give a lower bound for the Hausdorff dimension of the limb soup, right? So the hypothesis is going to be that I take my balls and I dilate them. So I have these balls and I make them larger. And I make them larger with this exponent S over N. N is the dimension, like the ambient dimension. S is the dilation that I do. So if this new limb soup, if the limb soup of the inflated balls has full netted measure, so if it covers the space, then the theorem says that you have a lower bound of the Hausdorff dimension of the original lim sup with this S, right? So let me tell you a brief example to see how the usefulness of this. So the Jarnik-Besicovitch theorem is a classical result in Diophantine approximation. So I want to look for the irrational numbers that can be approximated by infinitely many rationals P over Q with an error at most 1 over Q to the tau. And tau is 2 or larger, okay? So the classical Dirichlet approximation theorem tells you that if you put here a 2, so 1 over Q squared, then this is all irrationals, right? The Jarnik-Besicovitch theorem tells you that the Hausdorff dimension of this set with tau is 2 over tau, right? When tau is 2, then this is 1, the whole real line, let's say. When tau is larger, then the dimension is smaller. And this is kind of tricky to prove, right? And the original proof is not short at all. But with this principle, it's very easy. It fits in the rest of the slide. So because you can actually write this set as a lim sup of balls. Why? Because X is in infinitely many balls of center P over Q and radius 1 over Q to the tau, right? So this is your original lim sup. So now you take the balls, and you dilate them. You dilate them with 2 over tau, so that you get the radius turns to 1 over Q squared. And the Dirichlet approximation theorem tells you that the lim sup of these balls with Q squared is the whole, well, all irrationals at least. So of course it covers the whole space. It has full negative measure. Well, and that's all. So this 2 over tau exponent gives you a lower bound for the Hausdorff dimension, right? So this is great. I mean, it's super easy to prove this in principle subtle result.
Do we have a reverse of the Anna's paper theory there?
What do you mean? What do you mean reverse?
So this seems to me, if we have some Lebesgue, positive Lebesgue measure, then we can say something about the Hausdorff dimensions, right? And I mean, there are competing the Euclidean Lebesgue measure and the weird Hausdorff measure, and but can we get something reverse from Hausdorff dimension, and then we have something we are familiar with the Lebesgue measure?
So I guess the point is that usually the tricky thing to know is the Hausdorff measure, right? Usually the Lebesgue measure is easier to compute than the Hausdorff measure. So I would say that's the whole point of this theorem, that you take the difficult Hausdorff measure case to the easy, well, whatever easy means. Sometimes it's not that easy, but easier Lebesgue measure case.
Okay.
That's the idea of this principle.
Okay.
Right. So I want to tell you how we can use this principle in Bourgain's counterexample when you go to the fractal case, right? So remember that the set, the sets of Bourgain were unions of balls, right, centered at rationals. But in the Jarnik-Besicovitch case. But the point is that here you don't really have balls, right? You have different radius in the first variable, and 1 over square root of r, and 1 over r, a different radius in the rest of coordinates. So you really have rectangles, right? So the previous, the mass transference principle is from 2006. So right this year, Wang and Wu proved a generalization of that to rectangles. And the idea is just the same. So you take your original one, your original sets, and you dilate them. And now, of course, since you have several directions, you dilate each directions differently. R to the A1 and R to the A2. If this dilated set has full measure, and this I code it like this because this is a little bit more technical than this, but essentially the idea is this. Then, well, it gives you a lower bound for the dimension in terms of the dilations, A1 and A2. And in this case, it's a minimum of 2 points. Right? So the idea is the same. The only thing that we need to do is to check for which A1 and A2 this thing has full Lebesgue measure, right? So yeah, that's what we're gonna do. Well, I wrote here like a little bit of more like a change of parameters, which is not really important now because I'm running out of time. So let me just say,
you have 5 minutes more.
Good. So yeah, the point here is that I just take, like, remember the parameters were D and Q. So I'm rewriting them in a more convenient way, U1 and U2, where U1 and U2 are really like some powers. Okay, it's just more convenient. And this means that for the parameters U1 and U2, I have some restrictions in the plane U1, U2. So I can take in principle any parameter here, right? So let me go to the measure of the set. Remember, I have dilated the set, so I want to see that it has measure 1. Like it has full Lebesgue measure, right? So let me formally just count the number of balls that I have and compute the measure of each of the balls. Formally, this has to be justified, and it's kind of technical. But formally, you get this expression, you rewrite everything in terms of U1 and U2, and you force it to be 1, right? So that gives you a restriction for the dilations exponents A1 and A2, right? That is what I'm writing there, right? And then there is one more technical restriction, which is not really relevant, but it's gonna reduce the available space here for the parameters to this set. So what this says is that if you take any parameters in this yellow set and A1 and A2 satisfying this identity, then you can use the mass transfer space. And that gave you a lower bound, right? Which in this case, it was a minimum, it collapses into one expression, depending on A1 and A2. But it turns out that A1 and A2, you have it here, you replace it, and you get a lower bound in terms of the parameters. So, and you are essentially done, because this is what this is telling you is that if you, from the beginning, you fix alpha and you force the Hausdorff dimension of the set to be alpha, right? So you got a relationship between alpha and the parameters. So this is gonna tell you that every like U2 of this kind, every parameter of this kind is gonna give you a set of divergence of Hausdorff dimension alpha, what you want, right? This is in this picture, this is essentially saying that if you fix alpha, these are vertical lines in the U1, U2 plane. So any parameters in this vertical line is gonna give you a set of dimension alpha, right? This is what you want. And the Sobolev exponent, well, you just, this is the same as in Bourgain. You do the computations, you rewrite them in terms of U1 and U2, and you rewrite this in terms of alpha, because you know that you have this expression. So you get the fractal result, right? In particular, when n is alpha, this is 0, and you get the n over 2 n plus 1, which is Bourgain's result, right? So let me just finish saying that this is the classical Lebesgue result. So over n over 2n plus 1, you have convergence. Below that, you have divergence. So if here I put the Hausdorff dimension, then this is the situation. This is how these two results translate to the fractal case. And the one that I just explained to you is this red one. So you see that even if in the Lebesgue case it's closed, in the fractal case it's not, right? So exploiting this idea a little bit more, this is work in progress, but like together with Felipe, again, we think that we can like we can do a little bit better than this. Okay, this is still work in progress. And the last thing is that, well, that essentially the same ideas apply for this generalized phase that was tackled by Anchu and Pierce in the beginning of this year. The only change is that instead of Gauss sums, now you have Veil sums, because this is not 2 anymore, it's k, so you have n to the k instead of n squared. They can deal with that, and we use the mass transference principle in a similar way. It's a little bit more complicated because now the pictures are like this, the lines are not vertical, are bent, but you can do it, and we get the results, which are less clean than in the Lebesgue case. Different regions, it's not easy to write them in a clear way, but this is the pictures that we get. But this is essentially what I wanted to tell you. So I'll stop here, and thank you.